For our project, we decided to use a sailboat. So in our video, you can see us jibing. A sailboat tacking or jibing involves maneuvering against the wind by changing the angle of the sail relative to the wind direction. The boat's motion is influenced by wind forces acting on the sails and the keel, along with hydrodynamic forces in the water. This system is considered continuous. This is because of the continuous interaction of the wind and water with the boat dynamics.
This first photo demonstrates three separate reference frames, one of the water, one of the boat, and one of the land. The next diagram demonstrates why the land is considered inertial. It's not moving with respect to time, whereas the water, because of the current, is moving, and also the boat is moving at an angle theta in the x direction due to our sailors moving in the boat and their maneuver.
To cause the boat to roll, we work together to throw our bodies on one side of the boat. This causes a torque. If we were to consider just the mast of the sailboat, the angular acceleration of the mast would be 2.65 radians per second squared. This does not account for other factors like the moment of inertia of the hull, the wind resistance on the sails, and the water resistance on the underwater foils. Analyzing the video, the average angular velocity of the maneuver was 0.5485 radians per second.
The sailboat system uses instrument and visual inputs paired with manual maneuvers. While most small sailboats do not contain sophisticated navigation equipment, GPS and anemometers are regularly used on bigger yachts. GPS receivers on sailboats rely on satellite signals to determine the boat's precise location and velocity. These calculations are established within the Earth-centered Earth-fixed reference frame, providing a stable coordinate system with the Earth center as the origin. The inputs given by the GPS are usually converted to the northeast down frame to determine a corresponding course and heading. Concurrently, the anemometer gauges the speed and direction of the wind, allowing sailors to establish an appropriate sail angle. Sailors manipulate the sail angle to optimize the sail's power, roll tack to move the sail through the air, generating more apparent wind, and move the tiller to steer along various paths and around obstacles. This relationship between the sailor and instruments transforms numerical inputs into a maritime action, ensuring the sailboat charts a precise trajectory.
The inputs of the system include wind speed and direction, which determines how the sailboat will interact with the wind, rudder position, which is controlled by the sailor, and initial boat position and velocity, which is the initial state of the boat before any adjustments are applied. The outputs of the system are the boat velocity and the direction and the position of the boat after maneuvers are made. The control law in sailing involves continuous and dynamic adjustments of sail and rudder angles based on real-time observations made by the sailor. While not a strict PID controller, the control law still exhibits elements of proportional, integral, and derivative control, such as adjustments being made based on current error or deviation from the desired state, accumulated errors over time influencing decisions made by the sailor, and finally reacting to the rate of change of error